Hi everyone, welcome back to ThursDev. Today I'd like to get a little bit more in depth about artificial intelligence as it pertains to games. In this episode we're going to be looking at breaking down some of the common themes in game AI, working out at least one way to design some rudimentary character AI, and over the course of the next few design and scripting focused videos, begin taking a look at how to implement AI functions in Unreal 4, both with and without using Unreal Engine's behavior trees. The first thing to really do when talking about AI in games is to define exactly what AI entails when you're talking about game development. Likely, most people watching this show will already understand the basic concepts, but let's just go over them anyway, as it will assist us in deciding exactly how we want to make use of it. So, artificial intelligence, as the name implies, is a system by which a computer program simulates intelligence or decision-making. On a broad scope, it describes a massive field of research in which very smart people around the world are attempting to create computers that think, even learn on their own. In the context of video games, however, we take a very specific cross-section of behavior simulation, and generally speaking are simply defining the way that a game plays itself when given a defined set of rules. Often, the computer will be playing the game by the same or at least very similar rule set to the person controlling the game. Sometimes it's used to create some very sophisticated proactive and reactive non-player characters, but on the whole, it's very unlikely that most video game characters would ever come even close to passing the Turing test. When designing artificial intelligence for a game, one of the most important steps for the designer right at the beginning of their planning phase is to define very specifically what each actor controlled by the computer is capable of doing, what hierarchy these actions fall in, and what the limitations of these actions ought to be. By definition, as the AI is part of the computer itself, it has access to all of the information within the game. This, by definition, gives the computer an unfair advantage over the player, as the only unknown at any given time to the computer will be how the player themselves are going to react to any given situation. What this means for the game designer is that not only do we have to set a number of instructions to react to player behavior, but we also have to create a number of conditions in which these actions can be taken, whether to avoid the game becoming unfair when the computer becomes infallible, or to avoid situations where the computer is just doing things that break the rules of the game. When dealing with a game that includes AI-controlled enemies like a real-time strategy or top-down hack and slash, generally speaking, the AI will only need to deal with a few individual behaviors: autonomous movement, target detection and selection, which is commonly known as aggro, attack behaviors, and disengagement. These can be very simple or very complex, depending on how many situations you as a designer want the game to be able to react to realistically. On our first pass, we're going to deal with only the simplest form that these should take: wandering, aggroing on an unfriendly target and engaging, and disengaging if the target escapes from them to return to wandering. If we can accomplish all of the above tasks, we'll have successfully created a very basic AI. After that, we can start iterating and building up something a little bit more sophisticated. I like to call this stage of AI zombie AI, because basically what it does is find a target and attack it until it can't anymore, and just wanders around otherwise. If we were actually going to be creating a full-on zombie game, we might want to consider some more sophisticated conditions for behaviors like detection of attenuated sound or different attacks based on the player's relative position to the zombie. But at its core, what we want is basically just a mindless AI that really basically just knows when it sees a potential target and can decide whether it's actually a target, and if it is, to move towards it and attack it. So before we get into laying down even a single blueprint node, it will help us to know exactly how we want each of these individual behaviors to, well, behave. Movement is fairly simple. We did it in, albeit a controlled by the player manner, 2 videos ago when we set up our top-down camera. This time, however, the movement actions will be autonomous, which requires a little bit more planning. So let's sketch it out. What we want is an AI-controlled character to walk from point A to point B. That's simple enough. We have the AI move to command to take care of most of the legwork here. But once it arrives there, the game needs to turn it around and send it back to point A, and it needs to keep on going back and forth. Once we have this behavior worked out, we can start to extrapolate and do things like patrolling a sequence of waypoints or choosing a random waypoint and going to it. But before we can even start with something like aggro, we at least need the unit to be able to walk around. And to be honest, if that's all you want it to do, the job is actually fairly easy. We can create a couple of waypoints using target points, which are basically like stage blocking marks if you've ever been in a theater production. The game knows that they exist, but the player can't interact with them in any meaningful way, so they're ideal for creating points to send an AI character to. They don't even actually show up when the game is being played. It would be a simple matter of giving the character a list of viable places to go, and then telling the player to walk to each of those places in sequence. It shouldn't be too tough, so let's open up the project and see how we're going to do it. Now, the last time we were inside UE4, we created an AI character, which we called the AI-based template. I named it this way because I'm going to use this character as the parent class of all the other AI characters. When I need to create universal stats or define events or functions that every single character in the game is going to make use of, like health, damage dealing, and so on, I'll define them within this character. The character itself will only serve as a template, however, and other characters will make up the majority of the actual characters that will be seen in the game. The reason we do this is going to become clearer as we continue, but suffice it to say that it'll be nice ultimately to have a single character template that can house all of our global character traits and functions, while giving individual characters the functionality they need individually. We're going to create two new actors as children of the AI-based template. I'll call these AI Human and AI NPC. The AI Human will be characters that can directly react to human input, while the AI NPC will be our computer-controlled AIs. The NPC is the character we'll be dealing with the most for the immediate future. Let's go ahead and open up our AI NPC blueprint and start building a patrol function. The first thing we want to do is to tell the NPC what to consider a viable target point, and then tell it which among the viable target points it has it should use as its destination. To do this, we'll need to create a reference variable and an array. In a blueprint, as before, you can add a variable by clicking the plus button over here, and then after defining a name for the variable, in this case destination target, selecting a variable type. As always, Unreal 4 has a very useful search function, so we'll type actor, since target points are child classes of actor. Then, once we've found it, we'll select the reference type. This creates an open-ended reference to an actor, which can be a target point that we can change at runtime, which we can, in turn, set as the destination for a move action. We'll also need to create an array of actors, which can be done by creating a second variable, and then clicking over here this array button, telling the editor that instead of a single item, it's a group of items. This will be called target point array. An array, for those who aren't familiar with the term, is just a simple list of items that can be referenced after it's been created. Now that we have the variables that we need, let's go up to the begin play executor and attach a get all actors of class node to it, like we did with our brute force move command that we created before. As before, this tells the game to check the entire level for instances of a certain object. In this case, we want to define the class to search for as target point. Also, as before, we'll create a for each loop node. Now, we'll need to get the array that we just defined. From the list of variables, we can hold the control key and drag it out onto the blueprint. Normally, when we just drag from the list, it asks us whether we want to get the variable or create a set variable node. In this case, we only need to get it. From here, we'll pull another wire out and create an add unique node, then wire it into our for each loop. Sometimes you'll want the array to be able to contain multiple references to one thing, but when we're creating a straight up list of items, we don't need dupes, so we'll just use add unique. What this has accomplished is to tell the NPC AI, when it's spawned, to get a list of all of the available target points and remember them. Now, let's explore creating functions. Because this is something that we may use in multiple places, let's move back to our AI-based template for this one. Now, functions are basically events with common uses that can be called in multiple places. In this case, we'll create a simple function that checks an array for an item, increments it, and returns the incremented reference so that we can easily reset the reference. This will allow us to get the AI's current waypoint, then tell the AI to check the next item on the list and give us the next waypoint to set as a target. Let's call this the getNextInArray function. As you can see, after we open it up, it opens a brand new graph, unique to the specific function, as opposed to being part of the event graph. The function is going to need both inputs and outputs. Like before, we want to tell the game to accept an input of an actor array, which we'll call reference array, and the actor reference, which we'll call reference to increment, and to output an actor reference called incremented reference, which will be attached to a return node. The function is also going to need a temporary local variable that I can set as an output reference, which we may as well call output reference. The difference between local variables and normal variables is that local variables are only relevant to the function that they're defined within and don't affect anything outside. So, now that we've done our function setup, let's pull a wire from the array pin and get a find node, attaching the reference that we want to increment. This will get it within the array. From the out pin, which is an integer showing its position or index within the array, we'll add a simple add node, adding 1 to the index number, and then a get node, which will allow us to find an object at the index specified. This gets the current index, adds 1, and then returns the next item in the list. Now we could just output this to our return node, but in its current form the function would return a null or invalid reference once we got past the last item in the list. Instead, we want to add just an extra step by adding an isValid checking node, which will see if the reference returns a valid reference or a null reference. If the next item in the list exists, or is a valid reference, we can use it to set our output reference, which is the variable that we set before. If it's not valid, we can get index 0 from the array, which is by default the first position in the array, and return it, effectively looping us back up to the top of the list if we get to the end. Again, we'll set the output reference here, and then get a separate get of the output reference variable because we can't wire two things into the same return node. And then we'll just wire everything together. Voila! A useful function to find incremental indexes in an array. I know this is a hell of a tangent from move actions, but trust me, this will pay off and we're very close to done. So, let's make use of our new function by going back to the event graph for the AI NPC actor. Back at our for each loop, we want to pull a wire out from its completed pin, meaning it should perform this action right after it finishes creating the array, and try out our getNextInArray function, which you'll find it has access to as long as we've compiled everything. From the AI-based template. We'll get both of our variables for input, and this will return the first reference point at index 0, since there's nothing to look for since it wasn't set in the first place. Now for the actual patrol part. Let's create a custom event. This is like a mini function on the event graph that you can call to do just one specific job. We'll call it patrol, and also set this one for an actor input, like we did with the function. We'll call it destination. Do you see where I'm going with this? Now that we have the patrol event, let's call it right above the getNextInArray function, wiring our output incremented reference directly to the patrol event. Then we'll get a reference to self, create an AI move to node, wiring our destination into the target actor pin of the AI move to function. 3 steps left, bear with me. Once the AI has gotten where it wants to go to, we'll call another getNextInArray using the same references. As a matter of fact, we can just copy-paste what we have right above us. The major difference this time will be the incremented reference output needs to set a new destination target, or it would just keep getting a reference to the same target point it was already at and just do a little AI move to jig on the spot. We'll create one final patrol node to loop the whole event every time it gets to where it wants to go, and voila. Let's test it. And there he goes. Back and forth. We can add in more target points if we want to, and the game will always cycle through all of the available. Now note that this is an imperfect system because the game will always choose how to order the array on its own, but it's a definite start. And that's all the time we have for today. So, I'll bid you adieu, and I'll hope that I get to see you again in the next video. Thanks everybody for watching. Take care.